All right, so I would like you to buckle up because this is going to be a long video. So you can decide how many, sittings you want to do this in, because I'm going to cover a lot here about the Proton NMR. It's all about Proton NMR. We'll cover the number of signals, chemical shift, pretty much everything, okay, in this. So you can do it in 2 sittings if you want to, but I'm going to make one video, okay, for this. So let's take a look at the NMR first, and I know you've seen this before, so I'm just going to mention it again to you. There are a few things that we will study. So here is the x-axis, which you can see is the delta scale, or the ppm, which is parts per million. So we're going to look at this. We're going to look at what kinds of peaks appear. So here, first of all, you can see there are 2 peaks. Okay, so we're going to learn about why we are seeing 2 different peaks over here. Then we're also going to learn about, okay, fine, here is it 1 peak or is it 3 peaks, right? So if you look at it, it's kind of split. Or is this split? Okay, is this 2 peaks or is this actually 1 peak? So we're going to look at that also. And the last thing we will look at is the height of the peaks. Okay, so 4 things. And then also, actually that was 3 things. And then why this peak appeared here and why did this come over here, right? So all these different things we have to cover, which is why this is going to be a long video, okay, for us. But that's what we're doing with the NMR. So first, some technical terms. So all of those things that I mentioned in the previous slide to you, they're all have technical terms for it, except for the first one. Okay, number of signals. How many signals are you going to see in NMR? Now, we've done some other spectroscopies, or even if you have not done them, you're going to do them. Different spectroscopies have different signals. They have different peaks or mountains, or whatever they have in their spectrum. But in NMR, the number of signals that you have will show you how many different protons there are, different kinds of protons. Okay, so we're going to learn about what is the same kind of proton, which is called equivalent, or different kinds of protons. And every signal that you see in NMR counts for something. Okay, so you cannot ignore it and say, okay, well, this doesn't matter, or I'm not going to assign this one. You cannot say that. Every signal has a meaning. So the number of signals that you're going to see is going to matter. So we're going to talk about that. The location of the signal, where it is appearing, is called chemical shift, and that was the x-axis, okay, the ppm. So that's what we're going to talk about. Then we will also talk about the integration. So I mentioned to you about the height of the peak. That height of the peak, the intensity of the peak, that is called integration, and that actually shows how many protons you have under that signal. We also call that area under the peak. So that area under the peak is calculated by the computer, so you don't have to do it. I mean, you can if you wanted to, but the computer can do it for you, but that gives you how many protons you're looking at. So you can imagine already how powerful NMR is, okay? You already can tell so much more from NMR than any other technique. And finally, we're going to look at what is called signal splitting or coupling. And in the coupling, what you end up seeing is what kind of protons are next to each other, which again is very powerful, okay? Because just the protons appearing by themselves is enough, but now you can even tell what's on the next carbon over. So that's even more interesting for us, okay? So we're going to study all of these things one by one. So first of all, number of signals. Okay, how do you get the number of signals? So the number of signals depends on the unique hydrogens that are on that compound. So when you look at a structure, you should be able to predict how many signals you're going to get. So the way I look at it is, okay, I have these number of hydrogens. Are they in the same environment, which in technical terms are called equivalent? Okay, so if these protons are equivalent, then they're going to be exactly the same. If they are in slightly different location, then they might be different. Okay, so we have to identify the different kinds of hydrogens that could be on any compound. Okay, so we're going to look at that, and symmetry is going to play a role in that as well. Okay, so equivalent hydrogens, for example, if you have an sp3 carbon, okay, all the hydrogens on that are going to be the same, okay, because it's an sp3, it's tetrahedral. So unless there is something specific going on, like it's a chiral compound, you know, or when it's something is cyclic, in cyclic also you can't have rotations going on, right? So those kind of compounds will have a little bit different, classification, okay, of hydrogens. But otherwise, if you have a straight chain compound, then hydrogens on the same carbon will be identical, equivalent, okay. That's how we would see. And then we will also look at the symmetry, okay. So of course, me talking is not going to help you. Me doing some examples is going to help you, okay. So let's look at some examples over here, and I just put the whole thing out here for us to see, so you can, there's no surprise over here for you. Okay, so the example I gave you first, okay, when we started was CH4, right? And that was methane. And I said to you, all of these protons are exactly the same because of the way they are connected. And that carbon here is going to be sp3, so every hydrogen is equivalent, which means what? It means you're going to see one signal in NMR. Now here I have butane, okay, so I want to take you through ethane also, okay. So here I should have probably put this one first, but it's okay, we're all here. So in the case of ethane, now if you look at all of these hydrogens, they're exactly the same hydrogens. How can you tell that? All you have to do is draw a line in the middle and see if they're symmetrical. And how you can see that is just fold the molecule on top of each other, right? And if you fold it, all the hydrogens are falling on top of each other, and if they are equivalent. That's how I look at it, okay? So which means that ethane also is going to give me only one signal. That's how I see it. That's how I'm teaching you. If you find some other way that's going to help you, then that's fine also, okay? The most important thing is for you to understand the concept of equivalent protons. Okay, so then when you get to something like propane, something like this, so propane, now I think I covered this also before, but I'm just going to go over it again. So propane now, if you put a line through it, this one falls right on the line. So, and I'm trying to draw symmetry. That's why I'm drawing that line. So it means that you have protons and that line, and that is one kind of proton. And then you have, of course, this kind, which this, if you fold on this line, this proton in the box and these protons in the box on the right hand side, they will all fall together. And so these 6 protons are equivalent, and then these 2 protons are equivalent. Okay, so which means you have 6 protons which are going to be in the same environment, and then 2 protons that are in the same environment. So which means you'll see 2 signals, okay, in there. So the same thing happens with butane. In case of butane also, here is the symmetry line, okay, and so I have the colors here for you. So the blue ones are going to be identical, and then the black protons are identical. Hopefully you're getting the gist of what I'm talking about, so it'll become easier for you. The next one I have here is cyclohexane, and cyclohexane, you can draw all sorts of symmetrical lines, and if you draw them, you will see that all the protons are equivalent, okay. And I mean, I can draw lines all over it if you want to. It will just make a whole mess, okay. So you can draw a line here, line here, line there, you know what I mean. So it's all symmetrical, okay, in there. So all the protons are exactly the same, and that is gives them one signal then, okay. So which means that really, what are you doing with the NMR with cyclohexane? If you're going to see only one signal, then it's fine. I mean, you can run it, but there's no point, okay, because the whole point of NMR is for you to be able to see different hydrogens, okay, on it. Okay, so here is another one. Now here you have different kinds of protons, so you can see the different colors I've given to you. So here is 1, 2, 3, 4 carbons, okay. And the second carbon, you have a methyl group. But the thing about that methyl group, this is actually what the structure looks like, okay. So this is kind of like an isopropyl group, although it's not, but it kind of looks like that. So that's why I have drawn the pink hydrogens in the same, because this methyl group and this methyl group is exactly the same, Okay, they're symmetrical. Why is it symmetrical? Because it is attached to a carbon which also has a hydrogen. It is attached to a carbon that is a CH2. So both of these are attached to the same kind of a carbon. So they are identical. So the 6 pink protons are going to be the same. The blue proton, which is this one right here, that's going to be different, okay, because that does not resemble anything else. The red protons, and let me erase this because it's getting a little messy. The red protons are going to be the same then, they're equivalent. Remember, this is an sp3 carbon. So in sp3 carbon, both of these protons are going to be the same, okay? And then the last methyl group here, those 3 are going to be the same then, okay? So what does it mean? You have 1, 2, 3, 4 signals, okay? In this one, I've written this wrong, so this should be 4 signals, okay? So that's how you figure it out. And then here is another one, the next one, which I have kind of a curvy line drawn through it, and that curvy line shows you the symmetry, okay, in there. So right here is the symmetry in the molecule. So this molecule, as bad as it looks right now, I mean, I wanted to show all the hydrogens, okay? That's what I was trying to do, but this is actually dimethyl cyclopentane, okay? 1,2-dimethyl cyclopentane. So what I did is I drew all the hydrogens out so you can see that. And really, I encourage you to draw the protons out whenever you need to, okay? Because unless you draw it out, sometimes you don't see it, okay? So draw it out if you want. And so here is the symmetrical line right in the middle. And so you have one kind of proton. These 2 are exactly the same. These 2 are exactly the same. Don't forget there is a proton here. So, okay, I have them in red here. And then these 2 protons will be the same. And then this is identical, 2 within itself, okay? So 1, 2, 3, 4, okay? So this is by itself. Those are the blue protons that you see here. Number 3, this is the same, these 2 are the same, and these 2. So you look at the symmetry line, and then from there on you can figure out how many signals you're going to see. Okay, so it's kind of messy, but I hope that helps you. All right, and then look at the other ones. I don't want to go through every single one of them, but look at the symmetry of it and see if you can identify how many signals you will get. And if I have anything wrong, then you let me know, okay? But I don't think I do. I think I'm fine except for that one that I had wrong up there. Other than that, everything else is fine, okay? So that's how you look at the number of signals, is you identify the equivalent protons, okay? That's your first task. So here is another solved example for this, and I can go through it really quickly, or you can do this on your own too. But here, so this is acetic acid and acetic acid. Though just by looking at it, you can tell that these 3 protons are the same and this one is the same, so that should be 2 signals. And then here, draw the structure out, okay? So if you have a molecular formula given like that, or a condensed structure, draw the structure out, because sometimes it's just not not clear in the condensed structure. So here you have, of course, the phenyl group. That's going to give you 1 signal. Then you have this as 1 signal, and then this as 1 signal. Okay, so that should be 3 signals. Okay, and there, don't forget there is no hydrogen here. Okay, don't confuse. So that's 3 different signals. Okay, so here is an ether. And here's an isopropyl group and an ethyl group on the other side. So how many protons? 1, 2, 2 different kinds there, and 1, 2, 2 different kinds here. So remember, we just talked about the isopropyl group, okay, on the other side. So this one, these 2 are the same. So this should be 4 different hydrogens, okay? So that's how you do this. It's kind of all straightforward, okay? Draw the symmetrical line if it is, and if there is no symmetry, okay, if there is no symmetry. So for example, you have something like this. Well, there is no symmetry in this molecule. So you will see 1, 2, 3, 4, 5, 6. You will see 6 signals. Okay, so that's fine. That's okay. That's how it's supposed to be. So keep it simple. So the next thing that we look at is the chemical shift. We looked at the number of signals. So now where do those signals appear? That signal appearance is going to be called the chemical shift, and that's the delta scale, or the ppm, the parts per million. How do you get the parts per million? Okay, that's what we're talking about now. So chemical shift is actually going to be in hertz. In a very raw kind of a way. Okay, so this is like nothing has been doctored, everything. So if you're looking at the raw signal, it appears in hertz. And usually the instrument is going to be in megahertz. Okay, so as I mentioned to you before when we were talking about the instrument, instrument can be 90 megahertz or 300 megahertz, 1000 megahertz. It can be in, whatever megahertz. So we're talking about a hertz scale on a megahertz radio frequency. So you can see how small that is. Okay, from 1 to the mega is 60, so that's pretty big difference over here, but that's how it's done. Okay, that's how it is. But the problem that can happen is that if you're reporting hertz, it will be in this kind of a scale, the black one. If you look, so 60 megahertz, for example, this is what the scale is going to look like. If you look at 300 megahertz, this is what the scale is going to look like. So if that's what's happening, and then if you and I need to communicate, let's say I have the 60 megahertz instrument, you have the better one, the 300 megahertz, and I am saying that, oh, I have a peak coming around 360 hertz. And you say, well, I have one coming around 1800. Well, we're talking different scales then, right? So we will not be able to communicate properly. And even though we might be getting the peak at the same place sort of in the location, but we are not communicating very well. Okay, so for that reason, what we do in NMR is we take that hertz frequency and we divide it by the spectrophotometer frequency. Okay, so when you do that, so take 360 and divide it by 60 megahertz, so that is then parts per million. Okay, because that's going to be then 60 over 60 megahertz 10 to the power of 6. Okay, so not 60, 60 is, it could be any number over here. So divided by the 60 megahertz, so that is going to be then parts per million. So now when you do the division and then I do the division, then we're talking about 6 ppm, and now we are happy because now when you say you see a peak at 6 ppm and I say I also see one at 6 ppm, now we are communicating. Okay, because now we're not talking in hertz, now we're talking in a ratio, and that ratio is going to be the same for you and I. If we are looking at the same compound. Okay, and so generally what we do, and the NMR, the raw data is going to be in hertz. Okay, that's always going to be there. So when you process your data, when you process your NMR spectrum, then the computer is going to do this calculation, and then it's going to give you the scale as ppm. That's called the chemical shift. That ppm is also referred to as delta, okay, which is that symbol. So either one is fine. So ppm, delta, scale, generally we just kind of, say both of those, okay, but that's kind of how it works, and that's the chemical shift. Now, the other part of the chemical shift that you need to know is that you're going to have a chemical shift from 0 to about 12. Okay, it can go to about 12. I've showed you about to 10, but it can go to 12. Okay, so that's going to be your chemical shift range then. So it's not you're getting something at 32 or 40 or something like that. No, that's not what happens. So it goes from 0 to 10. Okay. There are some other things that you need to understand about chemical shift, and as we go on, we'll talk about that. And remember that the referencing solution I talked about, TMS, that's going to be at 0. That's the rightmost signal. Okay, so when you're processing your NMR data, that's what you're doing first, is you're setting your chemical shift scale, you're setting your reference point. Okay, so now we all have the same kind of scale. Okay, so whatever instrument you have, that's chemical shift. Okay, so we've talked about two things. Okay, so we have talked about the number of protons, and we've talked now about chemical shift. So now the number of protons, as I said, if you're looking at something like methane or hexane, one signal, what are you going to do with that? Okay, and really not much you can figure out from just having one signal in the NMR. Similarly, when you have a chemical shift, if all the protons are going to have the same kind of chemical shift, then what are you looking at? You just have one signal then, right? Or you have a similar chemical shift. Essentially what that means is that you have one chemical shift, which means you have one peak. So that's not going to be useful for us, okay? And so what happens in the NMRs then is there's more going on here, and thank God for that, okay? So when you have your compound, and this is kind of why I talk about the environment, the way I do, is because it kind of helps me also to figure out how many signals I'll get and where the signals will be. So if you're looking at this, you can see that these two protons are equivalent. Remember that, okay? So these two protons are equivalent, and then here these 6 protons are equivalent. Now these 6 protons, they are looking at these 2 protons are looking at these 2. Now the other aspect here is the shielding and the de-shielding that's going on. There is no de-shielding going on here, but shielding meaning that these 2 protons are surrounded by electrons. Okay, so what's going on here? Okay, so remember we talked about the fact that you have a magnetic field, and then you have so many of these nuclei that are just randomly arranged everywhere. You apply the magnetic field. So depending on these nuclei, whether it is this one or whether this nuclei is this one, they're going to be shielded or de-shielded depending on how much electron density is around them. And so because of that, when the magnetic field is applied, they can be in different locations. And that's how you get the different signals. But that is also how you get the different chemical shift. Okay, so chemical shift meaning ppm. All right, so there's going to be that kind of protection, as you can say, if you want to, I mean, these two are protected by they're shielded by all of these electron densities. So how much electron density is around a proton will also affect where they show up, okay? And that's the whole fun about doing NMRs, is because you get all of these different kind of data from molecules. So here are some chemical shift values, okay, that you have. So you can see that something which is shielded, which means it has a lot of electrons around, like alkanes, they will come at 0.9 to about 1.4. So this is like, alkanes as in CH3 or CH2. So remember, here is your ppm scale. So this is 0 and this is going to be 12. Okay, so the alkanes are going to come around. So let me just write this. So alkanes are going to come around here. Okay, so this is called the shielded region. This is here the de-shielded region. So when you have something like this and alkanes are coming around here, that means they are kind of all shielded by electrons, okay? All right. So now if you see this one, this is coming from a methyl ketone, okay? So no matter what you have here, but here you have CH3, but this CH3 is now connected to a carbon that has oxygen in it, which means what? Oxygen is pulling electrons towards itself, de-shielding these electrons now. So a methyl ketone will appear now over here. So you don't have to remember this number. There's no point absolutely remembering that number. But the thing is that what I'm trying to tell you is that it shifted. This CH3 is not the same as that CH3, okay, because of that oxygen, and it caused the de-shielding to happen, and so the methyl group shifted here. Okay, that's what happened. So this is the kind of things that happen in NMR, is that these kind of protons, which you would think, oh, these are all the methyl protons, CH3s, they should all come around 1. No, they can all not come around 1 because they're exposed to different environments. Okay, they have de-shielding and shielding going on. So Now let's look at some of the other ones. Here is the one, oh, I forgot to put the triple bond here. So, okay, there's a triple bond there, alkyne proton. So an alkyne proton comes over here, and then let's go on. This is for phenyl. Phenyl comes around like 7 ppm, you know, so that's very much downfield shifted, okay? And this has to do also a little bit with how these molecules are aligned in the magnetic field, okay? So for example, we said about the alkyne comes around here. So how the alkyne aligns with the magnetic field versus how benzene aligns with the magnetic field is quite different, because see, the double bonded H alkene proton comes around 5, but benzene is coming around 7. So like there is no trend for you to remember here, okay? And so I tell all the time that there's no point in you remembering any of these things. You can remember some things, and I will tell that in just a minute also, okay, what you can remember, because there are some things, if you remember, then it will make your life a lot easier, okay? But you can't remember every single signal. It's not going to help you, okay? So other things I just want to mention here before I move on from this is that look at this aldehyde proton, it's coming around 9, and then the acid proton, okay, now it's attached to 2 oxygens here, very much deshielded, okay, and that's going to be coming around 12 ppm, okay? So alcohol is variable, right? You can see that 2 to 5 p.m. Like, where am I supposed to see this, you know? So I mean, how can you memorize these things when you don't even know where they'll show up? So here's what I tell everybody to do if you want to kind of remember some of these signals, okay? So what do you remember here? Let me write it for you, so that way you can make a note of it, okay? So here's your ppm. This is 0. Alkanes will come around here, okay? So you can remember that from about, you know, 0 to 1.5, okay? Then I also remember the benzene protons, and you can see that I completely skipped everything in the middle, because the middle part is it's just, you know, anything can happen. And then this is around 7. 9 is going to be the aldehyde proton. So if you see anything at 9 ppm, just close your eyes and say it's going to be an aldehyde proton, okay? And so then if you see anything at 12, you know it's going to be a carboxylic acid proton, okay? So these numbers, if you can remember, that is good. That's pretty standard, okay? So again, this is around 7, so I'm not saying it's exactly 7. It could be 7.2, it could be 7.4, it could be 6.9, depends on what is attached to it, okay? And that's why you can't memorize a lot of the other signals, okay? Because things will shift, okay? And we'll talk about that. But I need you to remember that this is the shielded region over here, and this is deshielded, okay, over here. So that's how the chemical shifts work. Okay. So this is what happens with the deshielding. Okay, so here's an example of this. So if you have methane, okay, so we talked about methane having all the same kind of protons, which then come around 0.2 ppm. Okay, so I mean, just like where alkanes, we said 0 to, you know, kind of 1.5, that's where they appear, so that's where they are. Now, as soon as you add 1 chlorine to it, look at the shift you get, okay, from it. So 1 chlorine means methyl chloride. Such a big shift, okay? So that's about 2.8 shift. You add 2 chlorines and you get even more shift. Another chlorine, so much more shift. This is chloroform, so much more shift. So which means that you might think, okay, this is alkane and this is also alkane, but this is not really alkane. This is haloalkane. Okay, this is not really, you know, alkane, sort of. This is alkyl halides. But you might think, oh, but you know, if these protons are appearing at 0.2 or 0.5, this one should also appear. No, it doesn't. Okay, because chlorine is very electronegative. Now, I gave you for chlorine. The chemical shift could be different for bromine, because bromine is not as electronegative as chlorine, and fluorine is more electronegative. So the shift may be even more. So there's no point in us memorizing all of these things. What we need to understand is how things are connected and how then these signals can shift. Okay, so that's what's happening. So again, let me remind you, if this is a, you know, if your scale, okay, if you have a scale like this is the shielded region, okay, and I'm writing it again because, you know, we talk about this all the time. This is the de-shielded region, okay? This is upfield. This is a new term for you. This is downfield. Okay, so when we say a signal is appearing downfield, we mean more towards the left. Okay, so now one other thing I want to tell you, shielded, remember, means that there is more electron density. Okay, so de-shielded would be when there is some electronegative element connected to the compound. Okay, that's one thing. The other thing I want to mention to you is this is more like high energy. This is low energy. Okay, generally we don't talk so much about energy in NMR. We talk more about shielding and other things. Okay, we don't talk about energy, so I mean that's probably one of the least important things here right now for us in our context. Okay, in other contexts they might be important, but not for our context. Okay, because our level is we're just learning. Okay, so we don't talk so much about the energy. We talk more about upfield, downfield. Okay, so here's an example of a carboxylic acid proton. So you can see that it is an offset meaning it's off the charts, you know, because the scale goes up to 10 over here. And so this is from 0 to 10. So for acetic acid, this CH3, which is connected to the carbonyl here, it's also coming at 2 ppm. It's not coming in the range for normal alkanes. So it's coming at 2 ppm. And then the proton for the acid, it's coming at about 12.5. It says offset by 2.5 ppm means 10 plus 2.5. Okay, so 12.5 ppm. So generally this is a very common thing to do in NMR, is cut off a peak and just paste it in the middle here, so you don't have to draw all of it because there's nothing here, right? There's no signal here, so why print out the whole thing when you don't need it? So that's kind of how carboxylic acid appears in there. Okay, so just to show you the downfields. All right, so here is a worked example, because that's another thing you have to do, is to figure out the most downfield shifted protons in all of these. I don't even know why I have acetic acid. We just talked about it, so you already know the answer. Okay, this proton is going to be the most downfield shifted. And then in the case of the chlorinated alkane, anything that's attached to the chlorine, those protons are going to be. Now remember, I've colored these two pink because both of these are equivalent. Okay, and then as you keep going down, then you know the things get more upfield. So this is most downfield, this is most upfield. That's how it's going to be. And then in this case where you have the ether, I've taken the same compounds again, you know, but anyhow. So in this case, you look at what is connected to oxygen. So you have a hydrogen here, you have a hydrogen here, but this hydrogen is surrounded by more electrons, so this one is more de-shielded. Okay, so these two protons, which are equivalent, are going to be then more downfield. And then cyclohexanediol, don't be fooled. It's not going to be any of the carbon hydrogens. It's going to be the oxygen hydrogen. Okay, that is the most downfield. The second one will be these, and these four should appear at the same, because remember there was only 3 signals in this one. Okay, so 1, 2, 3. The third signal, this is going to be the most upfield. This is the most downfield. Okay. So this is kind of an example of showing you the number of signals and the chemical shift. So if you look at the structure, I mean, the way it's drawn is kind of a little bit weird. Okay, so I can draw this again for you if you want. So here is CH3. This is the CH3. Okay, this is the CO, that part there. Then there is a CH2. Then there is a carbonyl here. And this is an ester. So this is this. Okay, CH3, CH3, CH3. Okay, so looking at this, you can tell, of course, that there are going to be 3 signals, okay, because these 3 are the same, all the 9 protons, I should say, I said 3 methyl groups. 9 protons are exactly the same. There is no hydrogen here. These 2 are equivalent, and then there is here. Okay, so there are 1, 2, 3 signals. So the question is like, which one is the most downfield shifted? And the most downfield shifted is going to be the protons that is surrounded by oxygens. Okay, and the ones that is surrounded by oxygens is proton number 2. So that's going to be the most downfield shifted. Okay, so C here, you can see that, C, right there. Okay, that's the most downfield shifted. And the ones that are most electron dense, which means that are surrounded by more electrons, are going to be the most upfield, okay, over here. So that's how the chemical shifts and number of signals are working, and I've made this even more messy, but I hope you understand, okay, how we're dealing with chemical shifts and the signals. Okay. So now we come to intensity of signals. We've done two things, number of signals, chemical shift. Now for intensity of signals is going to be integration. Okay, and integration is the area under the peak. Okay, how many protons do you have? So you can see in NMR, there's so much information we can get. Okay, and everything matters. Where the signal is coming, how big is the signal, and we still have to talk about coupling, right? So I mean, there's just so much information in NMR. Okay, so the height of the peak is considered to tell you how many protons you have underneath that. So look at this compound. This is an ether, a methyl T-butyl, or I should say T-butyl methyl ether. So the methyl here, the pink protons over here, 3 protons. These protons in the T-butyl group, 9 protons. Okay, so which means the ratio is 3 to 9, 3 is to 9. So that one is 1 is to then 3, right? That's the ratio that you have. So now if you look at the size of this peak and compare it to the size of this peak, is going to be 1 is to 3. That's how it's supposed to be. So here's what we do in NMR is you can look at the background. Okay, the background, this is graph paper. Okay, the background here, you can have it on plain paper also, it depends. But if you have graph paper, all you need to do is count the number of spaces you have in there. Okay, because it's graph, so you can count the spaces. On the other hand, if you don't want to do that, you can have the computer do your work for you. And that's what I said. The computer does so much work. So there's so much work involved after you have taken your NMR. So what is the computer doing for you? What the computer is going to do, once you say, okay, you want to do integration, it's going to give you this line that you can see right here. This blue line that I'm tracing right now, that's the integration line. Okay, so I'm going to erase it now. Now that you've seen it, once you get that line, then you sit on the computer and you decide, okay, I want to chop, and I want to chop right here as close to this as possible, because then what the computer is going to do is going to calculate the area under the peak right here. If you chop here and here, it's going to calculate the area under the peak here. So you might get some other stuff, okay, which you don't need. So you want to make sure you chop really close, okay, to the peak. So you chop here, and you chop right here and here. So once you cut it, then the computer is going to calculate. Now, what does it calculate? It calculates the area under the peak. It does not tell you how many hydrogens you have. You have to say, okay, I want to assign this peak 3 hydrogens. So which means you should have an idea of at least one of the peaks and be sure that this peak is going to have 1 hydrogen or 3 hydrogens. Once you assign that one peak, that okay, assign this peak to be 3 hydrogens, is going to calculate for all other peaks. Okay, so you don't have to do the math for all the other peaks, but one peak you have to be sure. Okay, so you have to know a little bit about your structure. Okay, so if you're doing some kind of synthesis, you know what you're making. Okay, the problem is when you have an unknown compound and you're like, I just don't know, okay, how many hydrogens there are. So in that case, you work a little bit on your analysis and then come back and you can always do integration later. Okay, but one proton you have to assign. Okay, one peak I should say, you have to assign and say, okay, this one has 1 proton or 2 protons. So that's how the calculation works for integration. Okay, so once that is done, then you know how many protons are going to be, because remember, when you have a singlet, when you just have a single peak, that single peak can have 2 hydrogens or 3 hydrogens or 1 hydrogen. And you can have, I mean, it's very hard for us then to figure out what's going on and how many hydrogens there are. But at least this, the area under the peak will tell you, okay, you have 9 protons that are in the same environment. Okay, and you have these 3 protons that are in the same environment. So it gets a little bit easier then to assign protons. So here is another example for integration. Okay, so this one is it's kind of like a xylene, right? So paraxylene and paraxylene, now it has the methyl group and a methyl group, and then the protons here on the benzene ring. Phenyl protons, remember, come around 7 ppm. So the benzene protons have 4 hydrogens and the methyl groups are total of 6 hydrogens. And remember that because this is highly symmetrical compound, you only get 2 peaks, okay, in there. So one peak is going to have the 6 hydrogen, and this one is not that hard to figure out, right, because you only have 2 peaks. So, and if you kind of have an idea of what kind of a molecular formula you're working with, then it's not so hard, okay. But at least, once you know that you have 6 hydrogens here and 4 hydrogens here, that tells you a lot. And especially for benzene rings, because benzene ring is 6 protons, right? So if you have 6 hydrogens here, then the integration can tell you a lot, because if you have a mono substitution, then you're going to have 5 hydrogens. If you have di substitution, then you're going to have 4 hydrogens in there. So the number of peaks, the number of hydrogens under the benzene peak can tell you if you have mono substitution, di, or tri substitutions in there. So there's a lot of information there, okay, that you can get. So just, another example of integration. You have to use all of these things that we're learning together, okay. So the thing is, like, right now we're learning step by step, but eventually you put it all together and you analyze a spectrum. Now for spin-spin splitting, coupling. This is like the most interesting part, because if this wasn't there, then NMR is just made up of single peaks, okay, everywhere. So for this one, I should just say to you that, whatever you're doing, just focus on listening to me, okay, because I know as it is, this presentation is very long, but this part here you have to listen carefully for you to understand how coupling works, okay, because coupling can be a little confusing, and if you miss one little thing, then it can be confusing. All right, so just focus a little bit here. So splitting is when you have protons next to each other, unequivalent protons. Remember, equivalent protons will not split, okay. So when we were talking about ethane, okay, so we had CH3, CH, ethane like this. So when we had ethane, we only had one signal, that's it, and that's it, poof, that's all you will get. But when you start having more protons in there, so even with propane, for example, okay, you have unequivalent protons. Those unequivalent protons are going to show some sort of splitting. And if you're thinking like, oh, but we have seen so many NMRs and we didn't see any of that before, that was deliberate. Okay, so in those cases, you had equivalent protons. There was no splitting going on in there. So it was very deliberate. Now there is a spectrum in which you can actually see the splitting, because you have unequivalent protons, and those unequivalent protons now will start seeing other protons in there. Okay, that's the whole thing. So you have protons that are next to each other. Okay, so here is a very simple molecule, and I just made a mess here, so let me go ahead and erase that. So here you have carbon, 2 carbons, one with 2 chlorines on there. Remember, chlorine doesn't show up, and then it has 1 proton A, and then here's another carbon with 2 protons and 1 chlorine. Okay, so obviously, you have 2 different kind of protons, so you have 2 signals. So again, even if you're doing something very simplistic, okay, that we have done so far, so let me go ahead and draw this out nicely for you. So you have H and Cl and Cl, and then here we have 2 hydrogens and 1 Cl. So you can see there is no symmetry in this molecule, which means that this proton is going to give you one signal, and these 2 protons are equivalent, so that will give you another signal. So which means you have two signals, and here are those two signals. Now, with what we have learned so far, let's look at one more thing, okay, before we get into splitting. And the other thing I want you to look at here is which one is going to be more downfield shifted. So this proton, which is connected to a carbon which has two chlorines, is going to be more downfield, okay, and that's what we see here. So the pink hydrogen is giving you this pink signal, okay, and that is more downfield shifted than the blue one, okay, or the two protons here, because that's connected only to one chlorine. So that much we have done so far, okay. The other thing we have done right now is, of course, integration, and you can see that here as well. So let me erase all of this. So on one carbon you have only one hydrogen, and on the other carbon you have two hydrogens, so the ratio here is 1:2. So this much you have already learned. Now what we are saying is that because you have two unequivalent protons next to each other, they are splitting. So how does this split occur? All right, and this splitting occurs because you have protons next to each other that are unequivalent. Let me say that again, and I'm not going to say it again, okay. Right now this is the last time I'm saying they're unequivalent protons, okay. So I'm just going to say that protons next to each other are going to split, okay. So how? Let me draw this nicely here for you and then explain this, okay, as to how this is working. So you have two hydrogens here and one hydrogen on the first one. So this one here, the first one, I've highlighted that. What's going on here? This hydrogen is looking at these two protons, right? Then these two protons are looking at just this one proton. It's like neighborly thing, okay, that we're doing here. So the yellow proton is looking at two protons. So now the thing is, when it looks at those two protons, what is it really looking at? It is looking at their alignment. Okay, what do we mean by that? So now when this single proton, when this proton is looking at these two, those two protons can be facing like this in the magnetic field, or they could be facing like this in the magnetic field, or one could be facing like this, one could be facing like this, or in the same way, one could be facing like this and one could be facing like this. Now these two are the same kind, right? Because one of them is aligned with the magnetic field. Here is the magnetic field. So I brought it horizontal instead of vertical this time. So you have something that is aligned with the magnetic field, against the magnetic field, and then one with the 50-50. So one proton is looking at all of these orientations, okay? So when it's looking at another proton, which means it is looking at three orientations, okay? What are the three orientations? One orientation, 2, 3. 1 is to 2 is to 3, okay? Is to 1, excuse me. So one orientation, there are two orientations here and there is one here. So 1 is to 2 is to 3, and so you end up getting a nice triplet. Okay, I'm going to explain a little bit more here, okay, in just a minute. Now, let's look at the other one. Okay, so the other one here, this red proton, this one that I'm looking at now. So this red proton is either going to be facing this way or it's going to be facing that way in the magnetic field, which means what? There are only two orientations. So if it's only two orientations, you will only see a doublet, okay, in here. So you only see two splittings, okay? All right, so now I'm going to erase everything, and now we're going to talk about this again in a very simple way, all right? Okay. Once you understand one of these things, then everything else is going to be easier for you, okay, to understand. So first time is always the hardest one. So here is hydrogen, chlorine, chlorine, and then there's two hydrogens, and then chlorine here. So remember what I said, this hydrogen is looking at two orientations. So the way we say how the splitting is occurring is 2 orientations plus 1. Why am I writing that? There. Okay, let's fix that. N plus 1. Now, the other part of this is that these 2 protons are looking at this one, 1 proton plus 1. Again, N plus 1. Okay, so 2 plus 1 is going to be a 3 split. 1 plus 1 is going to be a 2 split. Okay, so again, let's look at this one now. So the actual spectrum and now the actual molecule, because right now it's just showing you everything. Anyway, so H is looking at 2 protons, so 2 plus 1. This is going to give you a triplet now, because it's looking at 2 plus 1. It's going to give you a triplet. So the pink one is a triplet. These 2 are looking at 1 plus 1. It's going to give you a doublet. So the thing about splitting is it's not about how many protons it has. It's about how many protons is it looking at. Okay, how many protons are next to it? That's important, plus 1. Okay, so it's not about how many protons, again, what you have. How many protons you have yourself, that is integration. Whatever number of protons you're looking at, plus 1 is the splitting that you will get. And why is it plus 1? It always happens plus 1. And that is just to do with the orientations that you have. Okay, and again, what are these orientations? So again, if you have 2 protons, okay, or 1 proton, so if you had just this 1 proton, it would give you that one orientation. So here is another example, okay, of that. So here is the triplet, okay, and in the case of a triplet here, you can see very clearly right here how the orientations are working. Okay, so this is, I kind of drew this for you in the previous one. It was getting a little bit messy, so this one hopefully is a little bit clearer for you. So if you have 1 proton that is looking at 2 protons, those 2 protons can be aligned with the magnetic field, against the magnetic field, or then one of them is with or against, and then the other orientation also with it. Okay, so now if you, this is the theoretical aspect, okay, of what's going on. The practical aspect is what you're looking at, okay, which means that you're getting a triplet and a doublet or whatever. Okay, that's what you have to look at. So the theoretical aspect, if you understand, okay, is that what it is looking at and the orientations of the proton in the magnetic field, then it will be easy for you. Okay, so look at this example here that we have, and this example is also very simple. Lot of chlorines, and then you also have hydrogens there, so not too many hydrogens here, and it's a very symmetrical molecule. Okay, so you can see that the blue hydrogens, they are equivalent. And then the pink hydrogen, of course, is by itself, okay, right there. So that's, you know, you'll get 2 signals from it, one for the blue, one for the pink. Now just follow my, my voice if that helps, okay? So that pink proton is looking at 2 protons. So though if it's looking at 2 protons, it's looking at 2 plus 1 orientations. So which means that this proton is going to give you a triplet. These 2 protons, the blue ones, are looking at 1 proton. That 1 proton can exist in 1 plus 1, 2 orientation, so it's going to give you a doublet. Okay, so the blue proton is going to give you a doublet. The pink one is going to give you a triplet. Okay, so that's how it works, and you can see it very nicely. Now, sometimes what you have to do in NMR spectra is you kind of have to expand your NMR. So here what you do is you take the peak, you slice it out of the NMR, and then you blow it up. Okay, and then you paste it on there. So this is, and again, another one of those workups that you have to do. So now you can clearly see the triplet and you can see the doublet. Now, if you're wondering, how do I know it's a doublet? And how do I know that it's not two singlets? Again, how do I know it's a triplet and not three, single peaks in there? Okay, so a very simple thing you can do is you can look at the baseline, okay, for this, and look at the baseline here. The baseline doesn't match up, okay, and what I mean by that is that when you have two singlets, the singlets will be like this. If you have a doublet, the doublet is going to be like this, okay? So which means this is the baseline. So singlets here, you will see that touching the baseline. In the doublet, this does not touch the baseline, okay? There is a space there, so you can see there is a space here, so you know it's a doublet, okay? So similarly with triplet. So when you see signal splitting, you can just look at the baseline and then make sure that it's not actually two signals, okay, versus one. So that's one of the things over here. The other thing I want to mention to you before I move on from here and show you some more signal splitting is the beautiful symmetry, okay, of these splittings, okay? So remember I was saying just in the previous slide, this is a 1 to 2 to 1 ratio because this is one orientation, this is one orientation, but here you actually have two orientations. So it's a 1 to 2 to 1 ratio, and here you can see in the size of the peak, it's a 1 to 2 to 1 ratio, okay? When you have one proton, that one proton can be like this or can be like this in the magnetic field. So it's a 1 to 1 ratio. And look at the doublet. It's pretty much a 1 to 1 ratio. They're equivalent, okay, almost in size. So that is another beautiful thing about looking at coupling in NMR, is that the splitting is very, very symmetrical, okay? So this was just a doublet and a triplet, okay, where you see only 2 to 3 protons. Now let's go on to more splitting, because yes, there is more, because you can have more protons also. So here is the one for a quartet. Okay, so you've already seen a triplet before. Look at the triplet. Again, it's the 1 to 2 to 1 ratio. For a quartet, what are you looking at? Okay, in a quartet, you're actually looking at 3 protons. Remember, it's n plus 1. Okay, so you're looking at 3 protons. So here are 3 protons. So these 2 protons are looking at these 3. So 3 plus 1, that gives you 4 signals, or 4 splitting. Okay, I should say. Now, how do those 4 splittings appear? So here is what the 4 splitting will look like. Okay, so you have 3 protons. Remember, you have 3 protons. 3 protons all in one direction, 3 protons all in the opposite directions, okay? And then you have all of these different variations going on of how the proton is aligned with the magnetic field or against the magnetic field, okay? So here, let's say there are 2 with the magnetic field, but if there are 2 with the magnetic field, it could be those first 2 or the first and the last or the last 2. Okay, so I mean, it's I wouldn't say it's complicated. It's just that there are so many variations there. Okay, and that's why you end up seeing, all of these beautiful drawings for all these protons. So here is, for another set. So this ratio is 1 is to 3 is to 3 is to 1, right? One set versus 3 sets versus 3 and then 1. So which means that this here is 1 is to 3 is to 3 is to 1. Okay, this one was 1 is to 2 is to 1. So, as I mentioned in the previous slide also about, how do you know a triplet is a triplet and not 3 signals. So one is the baseline. The other thing is the symmetry of it. Okay, because usually, if you have 2 signals or 3 signals, they're not going to appear in this kind of a symmetry. Okay, so only triplets appear in that kind of a symmetry. So this is coupling. Okay, so when you have protons that are unequivalent next to each other, they will see each other in a different environment and then start to look at all of these orientations, which is generally going to be n plus 1 orientation. That's the splitting it will give. Now remember, again, it is about what they're looking at, not what they are, but what they're looking at. Okay, that's how you get the splitting. It's a neighborly thing. Okay, looking at your neighbors, sort of. So here is a table of all the splittings possible. So if there is no equivalent proton, next to a proton, then you just get a singlet. Okay, that's it. No splitting whatsoever, and that's just one peak that you see. If there is one proton that's next to anything, then you see a doublet, which is a 1-to-1 ratio. If there are two protons, again remember the n+1 rule. If there are two protons, you're going to see 2 + 1, a triplet, a 1-to-1 ratio. Okay, and for yourself, you may want to draw this out. I'm not going to draw them because I don't have enough space here, but you may want to draw these out. Okay, so you have a singlet here, you have a doublet here, you have a triplet, okay, over here, and then a quartet would be the three. If there were three protons next to something, then it's a, you know, this kind of a signal. And then a quintet would be 5. The thing is, you know, you have to maintain a symmetry. Okay, so here this is equal, this is equal, and then here these two are equal, okay, like this. And then the quintet would be, of course, uneven, so this is what it would look like. So these two are equal, these two are equal. You can see my drawing is beautiful. So then a sextet and a septet and so on, right? So sextet again is going to be symmetrical. Remember, it's 1 to 5 to 10 to 10 to 5 to 1. So I mean, you're not going to do this exactly, but you know, you can try and you know, try and get this kind of a signal. That's what a sextet would look like, and a septet would be when you have something really long in the middle. So there, that's the middle one. Then here, right, something like this. So 1, 2, 3, 4, 5, 6, 7. All right, so you have that kind of a splitting going on. Again, it's n+1. Okay, so what does 7 mean? 7 means that you have 6 protons that are the same. So how many protons are looking at those 6? It could be 1, it could be 2. That's a different thing. That's integration. Okay, that will tell you how many protons are looking at that. So you know, two different things. Keep it separate. Coupling is separate, and then integration is separate. Okay, so that's the n+1 rule. Now a little bit about the coupling, a little bit more here. So first of all, equivalent protons do not split each other. So you know, I just want to mention this again. So here, for example, in butane, you have these 4 protons that are alike, and then you have you know, these 6 over here that are alike. So what's going to happen is that these two are looking at these 3. So which means that you're going to see 3 + 1 kind of a split here. That's a quartet. And then the 3, okay, on the other side, those 3 are looking at the red ones. That's 2 + 1. So you're going to see a triplet and a quartet, okay, in there. The red protons themselves, they are all equivalent, so they're not splitting. Okay, so that's what the first point there is. Okay, so if you have equivalent protons, they are not going to split, okay, in any way. The only time they will split is if their orientation is so different, like as I said, in chirality, or in cases of cyclic compounds, because in cyclic compounds there is restricted rotation. That's when they'll split. Or when there's a double bond, then they're going to split because there is restricted rotation. And so even though they look alike, but they're actually not alike because their environment is going to be different. Okay, so that's something that can happen. You have to watch out for that. And then protons that are separated by 4 or more bonds will not couple, which means really what you're looking at is, if you're looking at the center carbon here, these red protons, they will couple with, you know, on the left, on the right, if it's not equivalent, but they're not going to couple with this. Okay, that's not going to happen. So it's just a neighborly thing, is just right next to the carbon. Okay, nothing after that. And the one other thing that's not going to happen is if you have a heteroatom in the middle, then it's not going to couple either. And here is an example of that heteroatom. So here you have an ether. So there's a CH3 group here and a CH2 group here, and those two are not coupling, okay, because of the heteroatom in the middle. So they are too far apart to couple. So which means it's more like a carbon-carbon effect, okay? So carbon next to each other, and then they have protons on it, then they will start coupling. Okay, so that's how it works. So I mean, in this case, it's once you start learning about coupling, the singlets kind of start looking boring, a little bit. I'm like, what am I supposed to do with this? Because a singlet can be just one proton or three protons or two protons in this case. So like, how am I supposed to know what the structure is like if it's not even splitting? So you kind of like start liking coupling a little bit. Anyhow, so that's that. So here is some splitting examples, okay, for us. So here's the benzene ring. This is ethyl benzene. So ethyl group, CH2CH3, CH2CH3, 2 looking at 3, triplet, 3, excuse me, quartet, 3 looking at 2, triplet. So a triplet and a quartet. Ethyl groups will always give you a triplet and a quartet. Okay. Now, when I talk about NMRs, I give you clues about what you should be looking at. So in the chemical shift, I gave you clues. Okay, look for, aromatic proton at 7, look for aldehyde protons, right? In the splitting, my clue for you here is if you see a triplet and a quartet, okay, then you have an ethyl group somewhere. Most likely you have an ethyl group, okay, somewhere. And see, the benzene protons are coming at 7. By the way, I didn't mention this, but I should mention it now, is that if you don't get any kind of clear splitting, that's called a multiplet, okay? And multiplet is that there is splitting going on, it's just that it's not very clear. Okay, and so you kind of get all sorts of a hodgepodge of signals, okay, in there. So that is called a multiplet, which is M. Okay, you can by M. So anyhow, so the benzene ring here is giving, a multiplet. This is integration of 5 because there are 5 protons, and then you have the ethyl group, okay, right here splitting. And then here in this case, where you have a ketone, the CH3, of course, is not going to couple with anything because it's isolated. There is nothing in there. So you'll see a singlet in there. And then the isopropyl group here. Now, stay with me. This proton is looking at these 6 protons. So 6 plus 1 is going to give you a septet. These 3 plus 3, the 6, are looking at 1 is going to give you a doublet. So an isopropyl group is always going to give you a doublet and a septet. Septet. So here's the septet and here's the doublet. Okay. Now the integration is going to be very different because this is looking at 6 plus 1. So it's looking at 6 protons, but it itself is 1 proton, but it's giving you a septet. Here is the septet. Look at how tiny it is, okay, because there is only 1 proton in there. And the doublet is so big because the doublet actually has 6 protons, okay, in there, because the 6 protons are looking at 1. So that 1 plus 1 is giving you the doublet, okay. So ethyl groups and isopropyl groups, very specific kind of splittings, okay, that you will see in the NMR. Okay, here are some examples. Again for us, oh look, our acetic acid is back. Okay, so here what will you see a splitting for that proton? So again, keeping it simple, this proton here, this is not going to couple to this one. It's going to couple to this protons on this carbon. Now I have not drawn these out. You should for yourself, okay, whenever you want to see splitting, it's a good idea to draw the protons. So when you draw the protons, there are 3 over here. So these 2 are equivalent protons, okay, so these 2 are looking at 3, so 3 plus 1 is a quartet, so that's what it should give you. So 8 should be a quartet. Okay, now in this case, which proton are we looking at? So I'm asking you for 2 protons here, for 1 hydrogen here and this hydrogen here. Okay, so I'm going to pick the blue one first because that one only has 1 carbon attached to it. Okay, this one there is no other carbon here, so it doesn't matter. These 3 protons are equivalent. These 3 are looking at these 2, so 2 plus 1, it should give me a triplet. The pink hydrogen is next to this carbon and this carbon is next to 2 carbons. So it's going to look at both of these protons. So this hydrogen is looking at 3 plus 2. Remember there are 2 protons here. So 3 plus 2 plus 1. So that's going to be a sextet. Okay, so this proton is looking at 2 plus 1 triplet. This one is looking at 5 plus 1 sextet. That's how it should be. So one hydrogen, the blue one should be a triplet, and the pink one should be a sextet. Okay, that's how the splitting is working. So now in this case, this one is an isopropyl group here, right? So this isopropyl, oh, we just did this one, sort of. So anyhow, this proton is looking at the 6 plus 1 septet. That's how it would be. And then the last one here, what proton are we looking at? We're looking at the pink one here. So if you're looking at the pink one here, these two are equivalent, don't forget. So if these two are equivalent, what are we looking at? We are looking at this proton, and we're looking at these two. So 1 plus 2 plus 1 quartet. Okay, that's how it should be. Now, how is that quartet? Is that going to be a beautiful quartet? Maybe, maybe not. Okay, that's a whole different thing. All right, because this proton is very different because it's attached to the oxygen. Okay, over here. So it might be a little bit different. So that quartet may not be as pretty, but it's going to be okay. You'll see a splitting of 4. Okay. Coupling constants are really very interesting, and I'm not going to get too much into it, but the thing is that if you have too many multiplets, okay, in your spectrum, too many triplets and quartets and whatnot, so if you have a structure, that's is something like this, and you have, let's say, an oxygen here, and then you have this one here with, excuse me, an ester. So here is an ether. And then you have an ethyl group here, and you have an ethyl group here. Now, both ethyl groups are going to give you a triplet and a quartet, right? But how do you know which triplet and a quartet belong to the ether part and which one belong to the ester part? So for that, coupling constants are really good, because these two, when they couple, they will have a very specific distance between those triplet and a quartet. And these triplet and quartet, when they split, that triplet and that quartet is going to have a very specific distance between these two peaks. So now we're getting into really deep NMR, okay? And that deep NMR is the coupling constant, okay, which is called J. But in any case, that's given in hertz because it's a very small number usually, okay? And so you can look at the measurements of the coupling constant for all your triplets and quartets, and then you can say, oh, this triplet belongs to this quartet because, the coupling constant is the same. Okay, so that's how you can use coupling constants in this like one instant. Okay, so one example of it. So, I mean, there is a lot more to NMR than just what we are doing. Okay, so here are some coupling constant values. And again, you don't have to worry too much because I usually don't give this at this point, but it's really very good if you want to figure out if you have cis or trans isomers, because look at the coupling constants. And then here's, geminal hydrogens. What does geminal mean? That you have a terminal double bond, okay, alkene. So if you have a terminal alkene, the coupling constant between these two is very different. Now remember, these two carbons are next to each other, but these protons are not alike, right? These two protons may have a different environment. These two protons will have a different environment. These two have a different environment. So they're all going to show you different signals, okay? And so it becomes a little bit more complicated with double bonds, okay, in there. So the coupling constants help to figure out if you have a cis double bond or a trans double bond, because in some cases, like when you do Wittig reactions, then you don't know, okay, whether you have a cis or a trans bond. So, and here now you can see for, ortho and meta substitutions, you can figure out if you have that kind of a substitution, because the coupling constant can tell you that. So it has its uses. So here is a little bit of an example of complex splitting. You can look at this, read it yourself, but the thing is that these three protons are not the same, okay? So if they are not equivalent, then all of these three are coupling in a different way. This is going to give you a doublet. The C is going to give you a doublet, so it's too much, what we say, complex splitting going on. And that complex splitting, you can see what it looks like. Okay, and so this is styrene, same molecule, but you get so many doublets because, everything is splitting with everything, okay, in here. So it seems like there is too much going on, although it is just a splitting effect. It's just coupling. Okay, that's all that's going on in here. But like, it's anyway. But that's what happens when you have double bonds in there. You end up getting a lot of different kinds of splittings, and you have to do a little bit more in-depth kind of a study, okay, for that. Here are some other unequivalent protons. So this one we already saw the spectrum for. Here's, when you cannot have rotations, like in this one, okay, there's conformation analysis. And, when you can't have rotations, then you have, hydrogens that are restricted in their motion, so which means that now they will couple in different ways, and so here in cyclic compounds you have restricted rotation, so these two, even though they're on the same carbon, they're not equivalent anymore, okay, because one of them may be next to the OH and the other one may be next to the other hydrogen, okay, depending on their locations. So this is when you start getting non-equivalent protons, even though they're on the same carbon, okay, and that's all I'm going to talk about this, because we need to kind of wrap it up a little bit here. So now for oxygen and nitrogen peaks, they can be variable, they're coming in some different places sometimes. So when they do, the nice thing about these peaks is that you can figure them out just by exchanging them with deuterium. Okay, so you take your sample, shake it up with a little bit of deuterated water, and that will exchange the OH and the NH proton with deuterium, and you take your NMR again, and if that peak is disappeared, then you had an OH peak. Because sometimes, like, is this a singlet? Is this where my alcohol peak is? You can figure that out, okay, using deuterated water. So anyway, and sometimes they come as a little bump also, so you can figure that out. Anyway, so here is hydroxyl proton, and of course, the OH and the NH peaks are going to show up, okay, in there. So here is, for example, the alcohol peak, okay, right there for ethanol. And here it is. In this case, this is a very, very pure sample of ethanol. So there's a lot of splitting going on in this. And that's kind of something that happens, You also need good instruments, okay? And I think all of these spectra that I'm showing you, these are all coming, of course, from one textbook. And I think they took all their spectra in mostly 300 megahertz NMR, okay? And so, I mean, this is pretty good resolution and very good spectra that you are seeing right now. So here's like a normal ethanol, where you would see a triplet and a quartet and a singlet. But in this case, in ultra pure, you're seeing a little bit more splitting going on, okay? Now, I mean, I wouldn't worry too much about this, okay, for now. Okay, here is the nitrogen proton, like a bump over here. You can easily tell this is nitrogen, but if you're not sure, just shake it up with deuterium. If it disappears, okay, fine, this is nitrogen then. The magnetic strength, okay, a little bit about the quality of the NMR, okay. So if you need to improve the quality, you need to improve two things in there, the magnet and of course the radio frequency. So if the magnet is really good, then you can also use the higher frequency for it, okay. So what does it really mean? I mean, I can go into the theory of it, and maybe you're not interested in the theory, but what you're doing in a very simplistic way is, if you're driving a fast car, like a Lamborghini, you need to have a good highway for it too. Okay, you cannot drive a Lamborghini on a dirt road. Okay, so if you're going to have a good magnet, you need to have good frequency also to go with it. So that's kind of what we mean by, these two things going together. If you have a good magnet and a good frequency, you get a much better spectrum. Okay, so this is 60 megahertz, this is 300 megahertz. So you can see here in the 60 megahertz that there is some overlapping going on, so resolution, not so good. But in the 300, resolution becomes really good, okay? So I can explain to you in a very basic term what's happening. Remember, we talked about the magnetic field and how the protons are aligned against or aligned with the magnetic field. So what happens is, if you increase the magnetic field, then the distance between them will also increase. and that's how you improve resolution. And then when you increase your distance, because your strength is increased, then you need to increase the radio frequency also. So now you have more energy difference between them. So definitely you're going to get a much better resolution. That's essentially the theory behind using a good magnet, okay, in there. So the better, usually we don't talk about NMR in terms of magnetic strength. We talk about the quality of NMR with the radio frequency. So that's why you see the megahertz there, okay? So which it kind of goes with it, that if you have a 300 megahertz NMR, you have a better magnet, okay? That kind of is hand in hand. So better frequency, better resolution. 2D NMR is really fun thing to do, and 2D NMR is really good when you want to do coupling for complex molecules. So we were talking about, like the double bonds and unequivalent protons. So in those cases, it's really good idea to do a 2D NMR. 2D NMR is kind of something like a GPS mapping, or GIS, sorry, mapping. So when you're flying above, a mountain range, then you can correlate from there the longitude and latitude and figure out which peak you're looking at. So that's kind of what you see, is a lot of peaks over here, and then you correlate them. So this is one dimension, this is the other dimension of the proton NMR, and then you correlate the peaks to say, okay, this is coupling to that, okay? And so it takes a little work, but otherwise it works fantastic. You also need a little bit more time on the NMR for this. Usually NMRs run, normal NMR, 20 minutes you can get a good spectrum, but for 2D NMR you need to run it for a longer time. So here are some problems. I'm going to leave this up to you. I'm not going to do them. You can send me the answers. Feel free to send me the answers. So there's 2 here, and I think there's 1 more over here. So you can solve these and send them to me. Look at the coupling, look at the chemical shift, look at the number of peaks, and then figure out. The molecular formula is very small, right? So hopefully that should help you, that you only have 3 carbons here to work with. All you need to figure out is then how to get the correct splitting, right? Which here is quintet and triplet, and in the other ones there were some different splittings, okay? So you can feel free to send me the answers. Okay, here are some worked examples for, just a very simple thing about how you can use NMR to follow a synthesis. I mean, not that we generally do this, but, if you're doing this, you would definitely not look for disappearance of any peak. But yeah, you can see that if you have an alkyne versus a ketone, you will have 5 peaks in this one and you will only have 4 here. But of course you're looking for splittings also, right? So you will see different splittings in the product than you would for in the alkyne. So that will help also, okay? And in this case, of course, you will have an alcohol peak, and in your product you should not have an alcohol peak. So that will help you to determine if you have your structure, and of course you look at other things as well. I think that's it. I know that was a big thing, but it's done. Okay, let me know if you have any questions.